Grundfos Distributed Pumping. By replacing valves with intelligent pumps, we use less energy while bringing more intelligence to your cooling system. A Grundfos distributed pumping system uses the maintenance-free Magna 3 circulator and low-pressure non-return valves to prevent backflow. The distributed pumps ensure optimum pressure and flow at each terminal unit at all times. This also allows the centralized pumps managed by a new control logic to be significantly downsized because of the distributed pumps. This new design delivers perfect cooling comfort when and where it is needed within the building.
Good afternoon, everyone, and welcome to AABC's Tab Talk webinar series. I'm Colleen McCain, Marketing and Member Engagement Manager with AABC, and I'll be your moderator for today's webinar. Thanks to all our members and non-members across the community for participating today, and a special thanks to Grundfos for supporting this webinar. I have a few housekeeping notes before we get started. If you have questions for our speakers, please use the Q&A button in your Zoom window and not the chat, and we will feed those questions to our speakers at the conclusion of the presentation. You can submit questions at any time. No need to wait until the end. If you have technical issues, please use the chat box to inform the panelists and we will assist you. And finally, concerning AIA Learning Units, if you are an AABC certified TBE or TBT, please allow 7 days for your CEUs to be uploaded automatically to your portal. Today's session topic is distributed pumping and chilled water systems. Our experts joining us today are Justin Garner from Engineered Air Balance Company and Pete Korzeniewski from Grundfos. Justin Garner leads the Engineered Air Balance Houston office as Vice President and Branch Manager and has over 18 years of experience in building, commissioning, and testing, adjusting, and balancing of HVAC systems. He frequently speaks for Associated Air Balance Council regarding TAB topics. He also sits on the ASHRAE Epidemic Task Force. Pete Korzeniewski is the Business Development Director for Grundfos Commercial Building Services in the Americas region. He has been in the industry for over 20 years and spends most of his time at Grundfos focusing on projects related to pump system control. He loves having the opportunity to work with people that are actively working with hydronic systems and share some of the different ideas that Grundfos is working on that might help make those systems work a little better. Now I'm going to hand it off to Pete to get us started. Take it away.
Thank you, Colleen. Appreciate it. All right, hopefully everybody can see my screen. And we'll get started here. So today, in talking about distributed pumping, we want to cover a few topics. So I'll get into in detail, a case study that we worked on that features distributed pumping design. To start that off, we'll talk about today's HVAC system. So where we are today, how we're designing systems. Then we'll get into the distributed pumping concept, how it's designed, how it's operated, and then again, talk a little bit about the reference cases and some energy savings data. So to take a look at the inspiration for this, we were working with an engineering school, Ngee Polytechnic in Singapore, and in particular, this Block 22 building that you're looking at is a mid-sized campus, 85-acre campus that is set up, and this was a relatively new building for the engineering school. It had some lab space and some other facilities for the campus, sort of a mixed-use building. Singapore being a very tropical climate, similar to southern parts of the US. And it was built, like I said, not too old. It was built as a Green Mark Platinum building. And in Singapore, as far as I've been able to research, a pretty close equivalent to LEED. Like I said, a lot of different load patterns of the building, 570 tons of chilled water, and a combination of 10 air handling units and 5 fan coil units. So the building was having a really hard time trying to maintain temperatures in the spaces. They're getting a lot of complaints from the occupants, and we're not achieving the design delta T that they had. And they weren't achieving it from day one and weren't achieving it a couple years later when the frustration really built. So they were looking for other options and sort of started working with Grundfos with an idea around replacing control valves with distributed pumps. Right away, when they made this change and turned everything on, they saw an increase in their delta T of about 30%, and they were using about 54% less pump energy than they were when they were using a larger primary pump set and control valves. So very pleased with the results, and we'll talk about that in a little bit more detail. But as I said, to get us started, Justin's going to take over and talk about today's HVAC systems, sort of the evolution that we have and where we are today with typical systems.
Thanks, Pete. Yeah, so we're going to just give a brief run through of the history of, in this case, chilled water systems. So up until probably, I'd say 15 years ago, this was a pretty common system. It's a constant flow system. Obviously, you can see here that you've got multiple chillers and primary pumps for the system. Those primary pumps would be constant speed. And then you would modulate your cooling loads using typically three-way control valves at each terminal. But the flow was always the same. So obviously, as your load decreased out at your air handling units or fan coils or whatever they may be, your delta T would decrease on your chillers because you weren't really modulating your chiller loading and you weren't modulating your pumps and your flow. Go ahead and go to the next one, Pete. With the advent of variable speed drives, we then started to see variable secondary systems, such as this one, whereby we would, in many cases, it was still constant speed primary pumps. And most of the time they would be matched to the chiller or boiler. And then you obviously have to have a decoupler there so that you can decouple the primary loop from the secondary loop. But what was nice about this setup was that you could match your secondary flow to the load and get or remove, in most cases, your bypasses. Some of these systems still had a remote bypass out in the system, but you'd have to have a building automation or some other kind of controller that was controlling DP or flow in the system. Oftentimes it was DP measured 2/3 or at the furthest point in the system to control your secondary pumps. The challenge with this system became if your secondary pumps overpumped your primary, your temperatures would start rising in your loop. And so it creates a different control strategy there, but it was a way to start reducing some of the pump energy, at least in the furthest parts of the system. Go ahead and go to the next one, Pete. So then we get to where we are in most newer systems today. And it's typically full variable primary flow. Many of our chillers today can vary their loading much more easily than they used to. And so nowadays, we see where we have primary pumps that are on variable speed drives that pump out into the remote loads. But you do still have to have a bypass. And one thing that we see on these systems oftentimes is that the bypass is oversized. So there's a good bit of design consideration that needs to go into these systems to make the bypass work, whereby you still maintain minimum flow on the chillers that are in operation. And there's some pretty standard strategies in the industry to do that. And then obviously you're still controlling your overall pumping to maintain a DP out in the system. You just have to make sure that you don't put your chillers into a low flow condition where they start cycling or surging or going into alarm and things like that. Go ahead and go to the next one, Pete.
All right, thank you, Justin. Just to summarize some of those points and to keep in mind, with conventional chilled water systems, and this applies to any future designs we look at, is that peak load, what we're designing for, only occurs, 1% of the time typically. And as we've seen, in recent news, Sacramento saw 115 degrees the other day. that, maybe a new design point or maybe something a little less than that, but we're going to design systems for that, but they spend very little of their time operating there. In these types of systems, we've got high supply line pressures and huge fluctuation pressure need to be managed. And lastly is commissioning a system, depending on the technology used, tends to be, fairly complex, and if not done properly, can lead to performance issues. So we look specifically at chilled water systems and what the pain points are. The biggest one, and Justin talked a bit about it, is the delta T issues, or those temperatures returning back to the chiller. If we're not giving the chiller the appropriate temperature that we had designed for, we're going to see a lot of issues with cycling, which are going to lead to other problems. We're going to have uncomfortable occupants, are going to have complaints. The balancing is going to be an ongoing issue that we're going to struggle with. And it's this, level of complexity and design relying on a lot of different components working together that makes things pretty difficult. And lastly, it's different types of pump management strategies that are typical in HVAC systems. There's lots of different ways to do it, and a lot of them don't work very well. So we're going to talk a little bit today about a simplification of that. If we look a little farther at low delta T syndrome, I think the audience here is going to be pretty well familiar with that, is that it really results from that trouble that we have with traditional balancing and control, and we have pressure situations or fluctuating pressure situations that occur in the system, and what that does to flow. And ultimately, those changes in flow that we struggle to control are going to affect heat transfer. And but basically, how do we maintain that? There must be a way to balance the system. What is the best way, to keep flow rate at the desired rate, independent of the different pressure fluctuations you're going to see in the building? And the most common technology used for this are pressure independent control valves, or in this case, for our conversation today, we'll talk about pressure independent control devices. So really briefly on pressure independent control valves and devices, is the pressure independent control valve came onto the market. It essentially became a 3-function valve, and it allows us to, we'll start here on the right hand side, allows us to do our flow control. So it's got a modulating flow control valve as a component of it. It also takes care of that pressure control. It's got the ability to sense that incoming pressure, sense changes, and eliminate that. And then lastly, it's a flow limiting device. The last thing we want to do as we're trying to control flow into our terminal units or air handling units is to overflow that unit. So if we look closer at a pressure independent control valve, we've got, that device which will eliminate those fluctuation in pressures that we see. Our top half is our actuator that we either have a manual setup or an automatic setup that will open and close to allow flow into our air handling unit. And then the bottom section is a differential pressure controller that's basically going to automatically detect any changes in incoming pressure and adjust to those changes in incoming pressure, delivering the flow that the air handling requires. And this has been a great addition to our industry, and allowed a lot of systems to sort of come under control and operate properly. But this kind of control comes at a cost. I don't think people think of valves as something that has a cost associated to it or an operating cost, but they do essentially use a lot of energy, and we'll talk about that. So if we're going to dig into that cost, we want to look at a variable primary pressure profile for a whole system. So for this diagram that you're looking at, if you can imagine a 25-story building that's sort of flipped on its side, and by flipping on its side, we can sort of on the left-hand side over here, look at the head or pressure requirement of the pumps. So if we take a cycle of our pumps in the system, before we go into the chiller, we've got our hot side here. I'm gonna, sorry, I'll get my laser pointer ready. As we start here on the low pressure side of it, this is essentially leaving our chiller, entering into our chill water pumps, and the pumps doing their job are gonna, in this case, 50 feet of total dynamic head to the fluid entering the system, and then we travel through the primary loop. So our primary loop is here, you see our bypass, and then return. So we're going to generate that head level into the building and start to hit our 25 floors, first floor, second floor, third floor, and so on. And as we go through this particular system, the water is going to travel down its loads or its zones, however the system is set up, and we're going to start to see where the pressure drop occurs. So what piece of equipment are using pressure? So this first bit of pressure loss is through the air handling unit itself, and the majority of this pressure loss happens through the control balancing valve. We enter the return back to chill to pick up more chilled water energy to start the cycle all over again. If we take a little closer look at the terminal unit itself to see what the pressure profile is there, we have here again the P max at design flow for this particular air handling unit, and then the component talked about the control valve, our terminal unit, the heat exchanger itself, and then the isolation valve. So as we travel through this, 2/3 to 3/4, 70% of pressure is required for this particular terminal unit by the balancing and control. I've got a bit of loss through the terminal unit itself, and then even lesser amount for that last isolation valve as we travel back into the system. So this is a significant amount of pressure that we need for good control of the system. And that control is expressed in valve authority. If we have a good valve authority in our system and the ability to control those pressure fluctuations and deliver the flow we need to have pump pressure. At maximum flow, we talked about that design point, that maximum flow rate for our system, we need 25 to 50% of the total system pressure drop that should be absorbed by the control valve. So up to 50% of the total system pressure drop being absorbed by the control valve. If we, for example, need 70 or 75 feet of head to overcome the friction loss for our design flow through our hydronic system, our chill water system, we've got to basically add another 75 foot of pressure loss for that valve to have the proper authority. And as you dig into different industry, different manufacturers' manuals on sizing and selection, the rules of thumb that I've been able to come up with and that seem common is a 1-to-1 ratio of system friction loss to valve head loss. So it's just a different way to say the same thing. But that is a huge amount of head required for these valves to operate properly. So how do we deliver an optimized delta T for our building without wasting hydronic distribution energy? Well, we do it with a pump. I think a little bit differently about systems is how we set up and balance the building loads. We might consider that a pump is easy to set up and has the capability to automatically maintain balance in the system, increase the delta T, and ultimately reduce overall energy consumption for the building. If we take a look at that same pressure profile for a distributed pumping layout, it's going to look quite different. The first thing you look here is the amount of head required for that primary pump set is very small. And in this case, less than 10 feet of head required, because we're only worried about pumping the mechanical room and the friction loss associated with the pump, chiller, and associated piping. So the second difference that you'll see here is as we generate the head from the hot side of the system through the chiller to the, pick up that chilled water energy and start traveling out to the system, is you're going to see a crossover here at the bridge or at the decoupler bypass, whatever terminology you use. And essentially in this system, we're going to take a route of low pressure. So we're going to travel out to the system, out into our zones at a continuing lower pressure than where we started. And that's where the distributed pump is going to pick up its job. So the distributed pump is going to turn on as the load requires it to and pump through those friction losses that you saw, those losses that you saw in that terminal unit. It's going to take care of that itself. And then get through the air handler, have an exchange of heat, dump its chill water energy, pick up some heat and humidity, and then travel back to start the cycle all over again. So a few subtle differences, but a very different pressure profile when we're looking at putting those distributed pumps out into the system. So let's take a closer look at a distributed pump. First off, components that make up a distributed pump system, and then the design of a distributed pump system. So if we look at the components, as you see here, we've got chillers going to be the same. What we're going to take a look at this first part in regards to the differences in are the primary pumps, and then we'll also take a closer look at the distributed pump and the other hardware necessary for that. So if we look at the primary pumps, it's basically a typical primary pump set with controls, and the controls are going to have two functions. We're going to have, first off, our priority is going to be around chiller protection, and then secondly, we're going to want to manage that bypass, which I'll talk about in a little bit. And when we're looking at prefabricated pump skids, everything is sized, for the load itself. The head is minimized in the distributed pumping system. And with these onboard controls, hopefully they're pre-programmed, and you've got the opportunity for BMS and different logging optimization. Here's a look at primary pump set in the drawing, blown up a bit. And again, we'll talk about this in a little bit. We've got some differential pressure sensors. We'll add chiller protection, and then we've got the 4 temperature control sensors that we'll need to add across the bypass. We'll talk about operation in a few minutes. On the distributed pumps, we're looking at high efficiency, intelligent pumps, improved hydraulics to aid in, our efficiency gains that we're looking for. We've got temperature control, and I'll talk about how we're going to control these pumps, but we're looking at outgoing air temperature or supply air temperature. And we're going to, will give us a much better heat transfer and more efficient energy distribution. Depending on how smart your pump is, you'll have some control features that allow you to get rid of other hardware in the sort of the near air handler piping. And then onboard controls, sensor controls that'll help you in the setup. One of the things to know about these distributed pumps and the size ranges that we're talking about is they're wet rotor pumps. And some people, people who design smaller heating systems, I think are pretty well familiar with this terminology. Others that spend more of their time on the chill water side may not be aware of this. But basically a wet runner or a wet rotor pump utilizes the pumped liquid to circulate and around the motor shaft to remove any heat generated by the electric motor. There is no separation here between the pump liquid and the motor electronic itself. So, which is normally the job of a mechanical seal in a traditional pump. So we don't have that mechanical seal. We don't have bearings that we need to worry about. So those wear parts or those moving parts that are typically the most common failure points within a pump are not there. The pumps are essentially maintenance free and oftentimes last well beyond the expected life cycle of the system that they're put into. The last piece of hardware is just a simple check valve. Ideally, we want to take a look at a check valve that's got a low pressure drop, but we're going to put that on the hot side or the return side of the air handler, just to basically ensure that we don't get any backflow in any air handlers that aren't calling or aren't, don't have load at that particular moment in time. All right, so if we look at those components and operations, we're going to talk about those similar areas. We'll talk about the distributed pumps and how to control them out at loads or out at the air handlers. We'll talk about our primary pump control, which will include chiller minimum flow protection, as well as 4 temperature bypass.
Hi, Pete. Sorry to interrupt.
So if
It's
we look at
Colleen
our
here.
Yep.
Pete, sorry about that. Some of our
Hi, Colleen.
attendees are saying they're having difficulty. It seems like you might be having some connection issues. If you turn your camera off, it should strengthen your bandwidth and you should come through a little bit clearer as far as audio goes. So would you mind just switching off your camera for us? Perfect. Thanks. That should fix the issue,
Yep.
but we'll monitor it on the back end here. Thanks, and sorry for interrupting.
Oh, no problem at all. Is there any way to tell, is that improved at all or about the same?
As of now, you're sounding a little bit better, but just carry on and I'll pop back in if it starts to go out again. Okay, thanks.
Okay, thanks, Colleen.
You're welcome.
So when we look at the different options we would have for distributed pump control, we're looking here, as you see, we've got our our distributed pump, and our air handler. So if we're looking for most of what we've looked at so far have been variable volume systems, and we want to look at supply air temperature. So the air temperature sensor that you see here in this image, and the supply air ductwork, as that changes, that will be our set or reference point. We'll speed the pump up or slow it down to maintain control. If we are looking at a constant volume system, in that case, we'll look at return air temperature. But ultimately what we're doing is taking, a 0 to 10 for that signal, for that temperature sensor, and then adjusting pump proportionately to meet that set point. All right, if we look in more detail at the options that we have for setup and control, the first one is what we sort of talked about here, is that we're going to take that 0 to 10 signal directly from that sensor and operate the pump accordingly. It's about the most simple and quickest reacting option we have. The next option would be through the air handler's DDC. So if we have the control capability there and we want to feed that temperature sensor into the DDC, then we would take our speed signal from the DDC, and we would also have the option to do the same thing through the BMS system. We would take an optional start-stop from the DDC, so we knew when to be on or off with that distributed pump. But it really is as simple as that. Those would be the three options, and those would be in order of preference for Grundfos anyway. What I have here on the right-hand side is a chart of a few of the points of data that are available when using a communications card with our intelligent pump. These are just a few of those points, and as we've gone out and installed our first systems here in the US, we've gotten a lot of great feedback from controls contractors on the amount of data that we have available when we're talking about a pump that is responsible for flowing that water, has integrated sensors and temperature sensors, pressure sensors, and an ability to estimate flow rate. It's a lot more that's available typically from a valve without adding any other hardware or without additional points on the BMS system. The setup for this, to sort of finish it out, we talked a little bit about distributed pump sizing is really just matched to the AHU, the air handler, or whatever the load is. So whatever the flow rate is for that terminal unit, that's the size pump we would select. The head the head requirement for the pump would be the friction loss from the decoupler or the bypass to the physical location of the pump itself. The control signals we just talked about, we'd give the pump a set point either via the pump's interface or via remote control. We have the ability to use our smartphones to see the control interface for the pump if it's in a high location or up in the ceiling, wherever it might be. And then lastly is a parameter within our pump itself called flow limit. So that would be another settable parameter which would equal what the max flow rate is for that terminal unit, in this case an air handler. So we wouldn't need an additional flow limiting device or anything like that to make sure that we don't overflow the coil. That would all be done electronically. So Justin, I'll turn it over to you for your perspective, from a balancer's perspective on that setup.
Sure. Thanks, Pete. From a balancing perspective, and even a building commissioning provider, or maybe even a design engineer's perspective, this is a little bit different. Obviously, we're still trying to control flow through a coil to achieve our temperature control in, say, an air handling unit. I know when PIC valves came on the market, and even some auto flow devices before that, and definitely this technology, a big question has come up. What's the role of the balancer with these types of technologies? Does manual balancing go away? Do we need water balance scope? And the answer is yes. While we don't do a traditional proportional balance on a setup such as this, you still have to have someone that's going to go through and verify the performance of the system. So this is just another pump in the system, just like the pumps that would be in your central plant or in other places in the system. You've got to verify their operation. We all know, I would imagine most folks on this call work in the industry and have a fair number of years of experience. And as much as we'd like to think that we can just put things in the systems and flip the switch to on and it would work, oftentimes that's not the case. So from a balancer's perspective, the main role with this system is to, number one, verify that we're getting design flow through the coil, and also to verify some of those parameters and things and so forth that Pete just talked about. The flow limit might not get set up correctly. There could be other parameters that may not get loaded correctly. And the balancer should be one of the folks in the team, the project team, that's going to verify that this pumping this piece of the system is working correctly. It's taking the signal from the BAS or from an independent sensor, and it's modulating appropriately so that it can be ready for doing functional testing or whatever it may be as part of the commissioning process. So short answer there is you still need the balancer even with this system.
All right.
I'll go ahead and turn it back over to you, Pete. I'm sorry.
Thank you. I was able, Weston was talking, to review some of the questions, and one of them I wanted to get now because I've got a drawing up that maybe can help with it. And I think Weston had asked if I could repeat how we sized the distributed pump. This isn't the ideal drawing for that, but basically, if you can imagine that distributed pump out at the air handler in the system, we want to size it from this point in the decoupler out to the load itself. In this case, we're talking about an air handler, and then back again. So whatever the design flow was for that particular air handler, its distributed pump, whatever the friction loss would be from this point and back again, that would be how we size that pump. So hope that helps answer that. But as we go and talk about operation, and we talk about the primary pump set and that 4 temperature bypass control you see here, here's a very exploded view to give you an idea of what I'm talking about. So we have our primary pump set over here. Of course, we have our chiller. The first thing I want to point out is that we have pressure differential sensor across the chiller. This is how we're going to establish the first priority for the pump controller. The first thing we want to do is make sure the minimum flow requirement for this particular chiller is satisfied. All right, and we won't do anything until that is satisfied. Once that is satisfied, then we'll look at this 4 temperature bypass here. So this is our exploded bypass with 4 temperature sensors on the supply and on the return. And ultimately what we want to do is maintain 0 flow across this bypass, and that would give us our balance system. So if we take a closer look, our balance system is represented by, an E temperature across the bypass. So our chiller is operating, we're going out at 44 degrees. All of that flow is going out into the system. All right, that chilled water is moving through air handlers, it's picking up heat, and it's returning at a nice 10-degree delta T in this case, and then flowing right back to the chiller. So the system is balanced, either full open or partially open. We've got, a good balance across it. The second scenario is if we're starting to see supply water mixing with our return water. So we're flowing supply chilled water back across the bypass into the return. At this point, our pumps, our building is shutting down. Everything is being satisfied, and we're not requiring the flow we need, and we're starting to push some of that flow back to the return side. And then we'd see that represented in this temperature, and therefore we would know to slow our pumps down. The last connection is that our return is being mixed with our supply water. So we've got return water coming back here. We don't have enough pump speed. Basically, we don't have enough flow in the primary. So we're returning it back here. It's being reflected in this temperature sensor on the supply side. And we'll know now to increase our pump speed. The building is opening up, more zones are calling, more loads are calling. So we'll pick up pump speed to satisfy that. And that's really it. That's as simple as it gets when it comes to, the different operating conditions. So now we'll take a look at some of our CapEx and OpEx comparisons to a standard system. So we talked about the 2 different pressure profiles, and in a comparison, we'll look at, what a high pressure profile system looks like versus a low pressure or a distributed pump looks like, and talk about that in a little more detail. So the dark blue here in this particular case represents our variable primary system. And then the lighter blue represents the savings associated with replacing those control valves with distributed pumps. And at 100% flow, we're starting to see a little bit better than 20% saves. As we go to 75% flow, which is where we're starting to spend more of our operating hours, we start to see a bigger return. And where we spend most of our operating hours at less than 50% flow, even down as much as 25% flow, that's where we see the most savings, and traditionally where you see, you know, your biggest problems in system operation. So if we look at this, you know, in that same building, that 25-story building, and we look at it as a you know, certain amount of working days for a chill water system over a period of time, we start to see that energy use. And in this case, we're looking at a 60%, 3% less pump power. So pump, that hydronic distribution pumping power energy that we're talking about would be 63% less in a distributed pump system by putting that pump power out at the loads, as opposed to a large centralized pump plant down in the basement and then reducing the excess pressures with mechanical devices. If we start to look at our CapEx costs and how this compares to a traditional system, our index or our baseline is here. So a traditional control valve with a balancing valve, think you know, a flow limiting type of valve. This would be our index 100 for material costs, for installation costs, and ultimately in commissioning and balancing. This is what we're comparing ourselves to. This is the most typical in the industry. And as I said earlier, the new technology that's actually been able to solve a lot of problems for people have been pressure independent control valves. So simply taking out those older style control and balancing valves and replacing them with pressure independent control valves, you're going to see a very significant increase in upfront material costs. The pressure independent control valves cost more than an older style valve. The installation cost is going to be a little easier, because remember that pressure independent control valve is a 3-in-1 valve. So you've got one valve to install as opposed to 2 or 3 different devices. And lastly, the commissioning and balancing of that is going to be a little bit easier, at least dependent on system type, compared to the index. As we compare a distributed pumping application, our pumps, the actual smart pumps themselves, cost about as much as the control valve and balancing valve combo. Installation cost goes up a little bit. We've got to bring a different electric as opposed to what the valve will require over. And then we've got that check valve to install on the return side. Commissioning and balancing, you know, would be the lowest. We feel it's the easiest of 3 options, bringing our index down equivalent to what we see most today, which is a traditional control valve and balancing valve, and a little bit less expensive than what we'd see on a total cost for pressure independent control valves. Now, this is from the studies that we have done, you know, from our perspective. Justin, I don't know if you want to add anything from a balancer's perspective on some of these costs, or at least the indexes.
Absolutely, Pete. Thanks. So this is a common, I guess, misconception in the industry. I get a lot of questions on this from design engineers and owners and things like that, especially with respect to water balance scope and things like that. I appreciate the fact, Pete, that you guys did not completely eliminate commissioning and balancing, because I've been told by others that pressure independent control valves, or even, you know, an alternate technology, you don't need to do water balance anymore. And as I stated in one of the previous slides, you still have to ensure flow. Just with a pressure independent control valve, you still have to ensure the valve is set up correctly. You still have to set the right DP set point in the system to get the valves in control. So you're not eliminating the testing and balancing cost, or definitely not the commissioning cost. I would say that these figures, depending upon the system, might be a little on the low end, but they certainly, in certain instances, the 55, 52 order of magnitude with respect to a traditional system may be accurate. I would say most systems, especially if you were going to blend heating water and chilled water together, it's probably going to still be a little bit higher than this, although there will be a cost savings in most cases, especially with respect to the balancing piece.
All right. Thank you, Justin. All right, and the last piece before we get questions, I want to talk a little bit more detail about the case study that I sort of started with and gave you very little details on. So we'll give you a little bit more detail on what went into achieving these savings. So if we take a look at it, there was 15 terminal unit pumps installed. So we took out 15 control valves and put in 15 distributed pumps into the Block 22 building at Ngee Polytechnic. The primary pumps we were able to reduce those from 7.5 horsepower pumps down to 2 horsepower pumps. So significant reduction in size and ultimately reduction in energy there to pump that primary. And then when we look at our energy savings, we've had the ability to look at this with the different conditions that we've had in the buildings. We have teaching weeks, exam weeks, and then break week. We've had full occupancy, partial occupancy, and then some breaks. So as we look at that through the different days of the week, this is where by combining all of that, we're able to see an overall 55% energy reduction on pump energy. Looking at the same comparison, that same occupancy use case, that's where we saw, and you'll see a little bit of differences. When we were off, we really maxed out our delta T, and when we were operating, we were still able to improve it by 30%. We saw an average of 4.5 degree increase in delta T. So we, as a pump manufacturer, talk about the energy savings associated with the distributed pumps and what it takes to move that hydronic energy around the building. But we were able to, in this case, improve the overall chiller efficiency by almost 3%. So, which is dollars and cents wise, a much bigger number, even though it's a smaller percentage rate. So lastly, if we look at our kW per ton numbers, for a baseline valve system or what the original condition was prior to the upgrade, this particular project went in phases. So they took out the valves and replaced them with distributed pumps first. We've got some operating time and some operating data there. And then lastly, they reduced the size of the primary pump set. So we got to see that piece come together. So you can see as we went from our baseline system to just changing out the distributed pumps, we had an improvement from a 0.041 kW per ton. And then with those distributed pumps alone, we were able to go to a 0.028 kW per ton percentage. Once we combine the two and then we right-sized or downsized the primary set to match the distributed pumps, we were able to get down to a 0.018 kW per ton, which is ideally, where you'd want a system like this to be tracking. And again, in terms of pump energy, we saw a 56% reduction in energy on that system. All right, and just to give you an update, as to what we're doing, we talked about the case study in Singapore. We rebuilt our headquarters, or we built a new headquarters in Houston, Texas, for any of you that are down in that area or spend any time there. If you'd like to see that, we'd be glad to have you there. But we built this with a chilled water and hot water distributed pumping system. And even this system, as a new system, we struggled with getting it dialed in correctly and balanced correctly. And the folks over at Engineered Air Balance were able to help us do that. In addition to that, our own building, we've got 4 other buildings that are either in construction or are now operational as we've gone through the summer. 2 of them in Valdosta, Georgia, that's the southern part of Georgia, and it's a judiciary building and a jail. We've got the Museum of Flight in Seattle, Washington, which is operational now, and we'll be beginning construction on a building in Salt Lake City, Utah shortly. So all of these systems are, like I said, either operational or underway. And we don't have the results quantified yet. Apologize for that. Maybe we can do that in a follow-up. We're getting great response from them, just amazing increases and improvements in delta T, which is the biggest one. So as we gather more data, we'll be happy to share those. And then outside of the US, we've got over 20 systems. It's actually more. That was the beginning of the summer, installed globally. And like I said, with all consistent success stories. If anybody has any interest in doing anything like this, we're currently doing modeling for systems. We're developing a tool that we are using internally, with our partner network to design systems and take some of that pump sizing and some of those questions away. It's done automatically within the tool itself. And then once we've designed the system, we can show a projected energy savings as compared to a traditional system and give you ROI type information, if that would be of use for you. With that, we're to the point of the presentation where we'll take questions. I think we've got a bunch of them in the Q&A.
Yep. We have quite a few, and we'll get to as many of them as we can. We have about 15 minutes left, so I think that will actually be plenty of time. So I'll just go ahead and we'll dive right in. Sound good?
Sounds good.
Okay, so the first question here, I'm going to try and fill in, there's a little blank at the beginning, but I believe it's how do you set the pressure limits for the differential pressure sensor?
I'll take this one. I think this one came in while we were talking about the variable primary and primary secondary systems. And please just append your question or add another one if I'm not answering it correctly. But typically this is done by determining what your static driver is in the system, or head driver is in the system during the balancing process. So you've got to get everything at design flow. Obviously, if there's any diversity in the system, you have to take that into account. And then the balancer would figure out how much DP is required to get flow to the I guess the worst loads, so to speak, in the system. And so it's a pretty standard balancing process to do that. If that wasn't what you were asking, then let me know and I'll try to expound on it more.
Thanks, Justin. All right, next question. Is it better to have the bypass line close to the chillers or out at the end of the distribution system?
You want me to answer this one?
Yeah, you can take it, and then if because we have a thought on this too, but I'm sure you'll probably say the same.
Maybe. So I would say that it's better to have it closer to the chillers. The purpose of the bypass is to maintain minimum flow, especially in a variable flow system. And so, in many instances, it's better to have that hydraulically located close to the chillers. You don't want to put any more flow out there, any excess flow other than what the load needs in your remote piping. And so that's typically the way that we look at it. Pete, I mean, do you guys see it differently?
Pretty much the same. I mean, our preference would be, as you said it, and we want it close, but we can deal with a more remote mounted bypass. We just sort of, make some other minor adjustments so it's still possible. The one thing I would say is that for us, we'd rather have the load or the head requirement from the pump standpoint on those distributed pumps. These are smaller pumps. They're all ECM motors or permanent magnet motors. So that's where our efficiency really is, rather than having the requirement of our primary set, which could be a significantly larger set of pumps, taking on more of the load than it needs to. So ideally, same as what you're saying, and that's where I think our preference would be. I think the next question, Justin, probably was in your part of the presentation earlier.
Yeah, so disadvantages of an oversized bypass, and how should a bypass be sized? Again, the bypass needs to be sized for minimum flow of the system. Obviously, depending upon how you set up we'll talk about a chill water system, how you've set up your chillers, you need to determine what is your minimum flow condition for your equipment. And that's how you need to size your bypass. It doesn't need to be, it's commonly sized for line size, or something significantly larger. And then we end up getting into control issues depending on the control strategy and things like that. But ultimately, at the end of the day, it needs to be sized only for minimum flow for the equipment.
All right, the next question here, it looks like I'm going to try my best. When we have many numbers of DP in the system, which one can overrule control pump operation? I'm not sure if y'all can see it on your end there, might be easier.
Yep, I can see it, and I can take a shot at it. And Justin, if you have anything
Okay.
to add, please feel free. I think the question is referencing distributed pumps. So in the system, so not differential pressure. So if we've got many distributed pumps out in the system, I'm assuming the question is which one would overrule, and they wouldn't necessarily overrule each other. They would act in conjunction to each other. Those distributed pumps, if you think about them in the larger system main itself, which is going to be a larger pipe diameter, each one is going to be sized to pull its own flow rate at that, through that common pipe, and then the pipes, of course, will reduce as it gets down to its load. But it will operate seamlessly whether there's multiple or all of them, we're at full demand, or if we're only at partial demand with very few. So it's not going to be a case of them needing to override each other. I hope that answers the question.
All right, thanks, Pete. And this next one's kind of stumping me as well. It says, case AHU is VAV system pump will fluctuate.
I'm assuming I'll answer as best, as I would read it, is that in a variable air volume system, we will, be looking at that outgoing air temperature. So if our target, at least in the drawing that I showed, was 55 degrees, if we're starting to see more load, things are heating up outside, and that temperature is dropping, we're going to speed the pump up to provide more chilled water through the coil to maintain that temperature, the ultimately the space temperature. So the pump will vary to meet any changes in the variable air volume system. I hope that answered it.
Thanks, Pete. All right, next question. How is primary loop pressure controlled along its length as the various secondary pumps modulate? Is there a danger of certain segments of the primary loop having insufficient DP?
So no, there's no danger in that. It's sorry, I'm going to the answers just so I can read it while I'm going. Oh, all right. The distributed pumps, even though I guess I lost, Colleen, where would I find the question? I wanted to read it again. I looked in the
Sure,
answers.
let me grab it for you. I moved it over a little bit too quickly.
Oh, I found it. I found it.
Yep, it's right in towards the bottom of answered.
Right. So the primary loop pressure, it's controlled along its length, or the loop in the primary is basically we're not necessarily doing it with a traditional DP like we would in a traditional system. Our first point of control is to make sure the chiller, if the chiller is on and the chiller is calling, we've got a minimum flow rate that's been set by the controls contractor, according to what the chiller's requirements are, or when the chiller manufacturer starts up their equipment. So that DP will be maintained if we have a call from the chiller, ensuring that flow rate. Once that is maintained, any pump speed or pump pressure being generated above that point, we know that there's something going out into the system, and we'll speed up or slow down to match the temperatures that are being returned by the distributed pumps. So hard to explain that without a diagram. I hope that at least touched on it a little bit. But if you wanted to submit, or an email or something, I think our information is going to be available. I'd be glad to have that conversation in more detail.
Yes, emails are included here in the presentation. So if there are any additional follow-up questions, you're welcome to reach out to either of the speakers. All right, thanks, Pete. The next question here. This distributed pumps required to be installed in every AHU?
Yes, that's a simple one. So when we look at buildings, there aren't always air handlers. So usually air handlers, call for a significant load. So each of those significant loads would require a distributed pump. When we get into smaller loads, maybe fan coil units or what we might see in a heating system, there's going to be terminal units out there that have very small flow requirements. So what we're going to want to do in those cases is maybe zone those together, group those together, and have one distributed pump handle a few of those smaller load. And this will all be design dependent, and something that if there's a building that you're in or looking at or have in mind, we'd be glad to take a look at that.
All right, thanks. Next question. What about the initial cost and power consumption when compared to secondary pumps?
Yeah, that's a tough one. But I think it's going to be very consistent to the primary pump set. So when you look at a secondary pump set in a primary secondary situation, again, your primary, similar to distributed pump setup, is going to be it's responsible just for the mechanical room itself. So then your secondary pump set takes care of all the piping in the building. So you're going to, again, design that for the worst case scenario, which is going to be full flow through the entire system or most of that entire system and all of the friction loss associated with it. And then those secondary pumps will have to be responsible for providing the pressure for whatever control valves and balancing valves you're going to decide to use. So the savings there, distributed pumps and eliminating those secondary pumps and the valves associated with them, is going to be very similar to the primary. In this case, if the primary pump set is sized properly, we won't have the opportunity to downsize it, but we'll have the opportunity to control it better. So maybe slightly less savings than we projected on a variable primary system, but very similar. So hope that answers it.
All right, next question. How could this work in a campus type application with multiple buildings? Could you have a temperature bypass with a control valve at each building and then use distributed pumps in the building?
So answer is absolutely yes. So we've looked at a few of these sort of district or campus style buildings already. We've got, I don't know a lot about it, but I know our Grundfos colleagues in China have a large district chilled water plant set up exactly in this manner. And it really just depends how you're doing your campus loop. Is it high pressure, high temperature if it's heating, or if it's chilled water, what are the pressures? And then you decide how you do your breaks in the building. Would you be able to just have that bypass and then pump within the building, or would you need some sort of pressure break device like a heat exchanger? So it would just change the configurations a little bit, but all very doable options.
Great, thank you. All right, we have a couple minutes left, so we're just gonna keep getting through some of these questions. The next one for our speakers is there a minimum maximum size of distribution system that makes the distributed pump system a better option than a variable primary?
Simple answer is no. I mean, it's a great option for small systems as well as large systems. And we've sort of looked at and then have installed both. So it is anywhere where, you'd have a traditional primary, secondary, with a variable secondary, we'd be looking at a variable primary distributed secondary, and a building type is, and any and all, would apply.
Okay, great. Next question. Do we need to verify the flow across the PIC valve during the balancing apart from DP verification?
I'll take this one. I think this is referencing just a PIC valve, not necessarily distributed pumping. And the answer is yes, flow does need to be verified. The first step, typically, depending upon the manufacturer, is to ensure that the valve is set up correctly or sized correctly. Various manufacturers do this in different ways. Some are electronic, some are on the top of the valve. But you've got to make sure it's set correctly for the appropriate range. And then obviously verify that you can get the appropriate flow through the valve using different techniques depending on the application. And then ultimately you have to ensure that the system maintains the minimum DP stated by the manufacturer at the most remote valve in the system, so to speak. Very similar to what you would do in a variable volume air handling unit system. So if you want more information on that, let me know.
All right, great. Thanks, Justin. All right, so we're at just about time here. We had a lot of really great questions. Thank you everyone for submitting. We will keep track of these last few that weren't answered and share them with our speakers today. Again, you can always email them any additional questions after the presentation. All right.